this video, we're going to think about slightly more complicated ones. And in particular, what happens if in the process of having an ether, we actually have a ring as opposed to just a long chain. So you could imagine a molecule that looks something like this. You have your oxygen. On this side of the oxygen, you have this carbon chain right here. You have a carbon chain like this, but then that chain bonds back to the oxygen. So we have a ring here. And so it's not obvious how to name this. You can't just look at this side and call it, methyl, and then that side and call it methyl as well. It's the same side. It connects back to itself. So how do you name this type of ether? So what you do is you just number it. You number it. You number the longest carbon chain like we've always done in the case of an alkane. So this is, we can start numbering here. 1, 2, 3, 4. And so this, if we just think about the carbon chain by itself, we know if it's one carbon, it's the prefix is met, meth. 2, it's eth. 3, it's prop. 4, it's but. So if this was just a carbon chain, we would call this butane. So if we just looked, if we only looked at this carbon chain right here, this carbon chain right there, you would call this butane. You would call this butane. But obviously, this isn't butane. We have this oxygen that's bonding to the 1 and 4 carbons of the butane. So to make that clear, we call this, and let me color code this part right here, this oxygen right there. It's bonded to the 1 and the 4 carbons. So we call this 1, 4, and this is our new word that we're going to learn in this video, 1,4-epoxybutane. 1,4-epoxybutane. And it doesn't just apply when the ether forms a large ring. It can actually form a little subset ring on a regular chain. So you could imagine something like this. Let me draw a chain of carbons. Let's say we have 5 carbons. 1, 2, 3, 4, 5. Just like that. And then let's say that between this carbon and this carbon, instead of having a double bond, this carbon actually bonds to an oxygen, which then bonds to this carbon over here. And obviously, every carbon has 4 bonds. The ones that we're not drawing, those are hydrogens. How do we name this? Well, same exact process. We start numbering. We actually start numbering the chain closer to where the oxygen is bonded. So we start numbering at this end over here. 1, 2, 3, 4, 5. So this is pentane. This is pentane. And then the oxygen is bonded to the 1 and the 2 carbons. So we call this 1,2-epoxypentane. 1, 2 epoxypentane. Now, in the last video, I told you that in general, ethers are fairly non-reactive. They actually make for good solvents. But what I've just drawn here is a special case of ethers called epoxide. So when you just have this kind of three-atom chain right here, where it's 2 carbons and an oxygen, this is a special case of an ether called an epoxide. This is called an epoxide. And this, unlike most ethers, is very reactive. This is very reactive, or another way you could think about it, it's very unstable. This is very reactive. So sometimes people kind of consider these separate from ethers. And the reason why very reactive is this 3-member ring right here. There's a lot of strain on these bonds. These electrons, these bonds don't like to be that close to each other. If you actually tried to make it with an actual a model set with molecules, you would have trouble making it bend enough to actually make this bond. So this is highly, highly, highly unstable. And there's actually an alternate way to name epoxides. The alternate way, so this is a completely legitimate way. You can name it just like an ether with a ring. This is 1,2-epoxypentane. But the alternate way is to pretend like you had a double bond here. That instead of this oxygen here, you had a double bond. If you had a double bond here, this thing would be called, depending how you want to name it, you could be called 1-pentene. 1-pentene. That's if there was not this oxygen here, but if there was a double bond here. 1-pentene would look like this. 1, 2, 3, 4, 5. This is the 1 carbon. So 1, 2, 3, 4, 5. So this is what 1-pentene looks like. We've learned that many, many, many videos ago. Sometimes it's called pent-1-ene, depending on which convention. This is kind of the more common one. But we have this oxygen here instead of this double bond. We have this oxygen here instead of this double bond. So instead of calling it just one pentene, we call it one pentene oxide. We call this one pentene oxide, just like that. So both of these are the names for the same exact molecule. This makes it clear that it's an epoxide. That's kind of the special ether that is more reactive. This is just a general way that we name any type of cyclic ether. So let's just do one more just to make the point clear. Let's have a cycle branching off of a cycle. Let's have an epoxide off of another ring, just to make the point clear that these aren't too hard to name, but the first time you see them, a little daunting. So let's say we have a cyclohexane ring right here. So let's say we have a cyclohexane ring. So left to it, so this is cyclohexane. But let's say we have a little epoxy branching off of it, just like this. We have that going on. So if we wanted to make it clear that this is an epoxide, we would essentially pretend, or first pretend that this is just a double bond. If this was just a double bond, this would be cyclohexene. This would be cyclohexene. Cyclohexene. If this oxygen wasn't there and instead we just had a double bond here. And you actually don't have to specify the number for just when you only have one double bond in cyclohexene, because it could have been anywhere and it would have essentially been the same molecule. But since we have this oxygen here instead of a double bond that's bonding to both of these carbons, we call this cyclohexene oxide. Cyclohexene. So this part right here makes us name this cyclohexene oxide. Or if we wanted to just name this as a traditional ether, the way we would do it, we would just name this. We would just name this cyclohexane, and put the epoxy in front of it. And put the epoxy. Either of these are valid. And once again, you don't have to number it because you could call it 1,2 epoxy cyclohexane if you made this the 1 or the 2 carbon. But it's going to be on adjacent carbons, and it could have really been on any of these two. It could have been on the 3 and the 4, and it would have essentially been the same molecule. So this actually makes it clear exactly what the molecular structure of the molecule is. Well, anyway, I thought you would enjoy that. And in the next video, well, I told you that epoxides are reactive, so I'll actually show you a reaction with dealing with epoxides.
It's possible to have ethers in a ring system, and there are many different types of ring systems that you can have with ethers in them. The one that's studied most of the time would be the epoxides due to their reactivity. Here we have the simplest epoxide, and one name for this would be ethylene oxide, because this molecule is made from ethylene, and that's where you get your 2 carbons from, like that. So you could call this ethylene oxide, or you could give this an IUPAC name. And since there are 2 carbons in it, for the IUPAC name, we start with ethane as our parent name. And we know that the epoxide forms between carbons 1 and 2. So we can go ahead and write 1,2 epoxy ethane for the IUPAC name. Let's do another one here. So let's put some more carbons on here. So we'll put a few extra carbons, and we'll name this using IUPAC nomenclature. So once again, find your longest carbon chain, right? So we can go ahead and find how many carbons in our longest carbon chain. That would be 1, 2, 3, and 4, like that. So we can go ahead and write butane for our parent name. So we can go ahead and put butane in here. I want to next number my carbon chain to give the lowest number possible to these substituents. So in this case, it makes more sense to number from the left. So I get 1, 2, 3, and 4 to give my substituents the lowest number possible. I can see now that my epoxide forms between carbons 2 and 3. So I'm going to write 2, 3 epoxy butane, like that. And I know that I also have a methyl group coming off of carbon 2. So to complete the name, all I have to do is write 2-methyl in the front here. So now I have 2-methyl 2,3 epoxy butane for my IUPAC name. So how do we make epoxides? We've already seen one way to do it, and in an earlier video we started with our alkene, and to the alkene we added a peroxy acid. And a peroxy acid looks a lot like a carboxylic acid, except it has an extra oxygen in there like that. And in the mechanism for the epoxidation of alkenes, we saw it was a concerted mechanism where one of those oxygens was added in here to form our epoxide like that. So check out the earlier video to see the mechanism for epoxidation of alkenes. So in this video we're going to cover another way to make epoxides, and that is using halohydrins. So to make a halohydrin, you also start out with an alkene, and we also saw this mechanism in an earlier video. You add a halogen and water, and we're going to add bromine and water. And we end up adding the OH and one bromine across our double bond. So we ended up getting an anti-addition of an OH and a bromine. Okay, so they're going to add on opposite sides from each other like that. Okay, so this molecule is called a halohydrin. And again, check out an earlier video for the mechanism to form a halohydrin. Once you form a halohydrin, you can use that halohydrin to form an epoxide. All right, so let's go ahead and take that halohydrin and let's see the mechanism of how we can form an epoxide from that. So I'm going to redraw that halohydrin. So I'm going to go ahead and put in the OH here like that, put my lone pairs of electrons, and then I have my bromine over here, and I'll go ahead and put in my lone pairs of electrons on bromine as well. And for right now, we can say anything could be attached to this, and we'll go into stereochemistry in the next video. So what we need to do is add a base. So something like sodium hydroxide will work. So we're going to add in sodium hydroxide, Na+, OH-. Right, so the hydroxide anion is going to function as a base. Right, so a lone pair of electrons on the oxygen are going to take this proton on our alcohol, and these electrons in here are going to kick off onto our oxygen. So let's go ahead and draw the result of that acid-base reaction. All right, so what do we make from that? Well, now we have our oxygen with 3 lone pairs of electrons around it like that, which give this oxygen it gives the oxygen a -1 formal charge. And we still have our bromine here like that, and then we still have these other groups attached to our carbon. So in the next step, we need to think about, again, the polarization in the bond between carbon and our halogen, right? Our halogen is more electronegative, so the halogen is going to take a little bit of this electron density in the bond between carbon and bromine, and therefore give the bromine a partial negative charge, right? This carbon is going to lose a little bit of electron density, so this carbon is actually partially positive. And so the alkoxide that we formed when the alcohol was deprotonated has a negative charge. It's going to function as a nucleophile. The partially positive carbon wants electrons. It's going to function as an electrophile, and we're going to get a nucleophilic attack by our alkoxide anion on our partially positive carbon. So this is actually an intramolecular Williamson ether synthesis. So if you think about it, right, if these electrons in here are going to attack this carbon, right, that would kick these electrons off onto your bromine like that, and it's an intramolecular Williamson ether synthesis where your alkoxide is the nucleophile in an SN2 type mechanism. So if we go ahead and draw the product, right, now this oxygen was bonded to the carbon on the right. Now it's also bonded to the carbon on the left, and the bromine left. That was our leaving group, and so we can see that we're going to end up forming an epoxide with this mechanism. So let's go ahead and do a quick problem here where we're forming an epoxide from an alkene, and we'll start with cyclohexene. So here is our cyclohexene molecule, and we'll make an epoxide 2 ways, right? So in the first way, we'll add a peroxy acid, and there are several that you can use. One of the most common ones would be peroxyacetic acid. So peroxyacetic acid, right, looks very similar to acetic acid, except you have an extra oxygen in there, like that. So it's epoxidation of an alkene. And when we draw our product, right, so let's go ahead and draw our product. We form an epoxide. And I'm going to go ahead and draw the product with a wedge here, right? So there's an oxygen coming out relative to that plane. And if we go ahead and name our product, right, so the parent name would be cyclohexane, and our epoxide would form between carbons 1 and 2, so we could go ahead and name this as 1,2-epoxy cyclohexane, like that. Let's go ahead and 2-cyclohexene. Let's do another reaction. Let's start with cyclohexene, and this time in the first step, we'll add some bromine and some water, and that will form our halohydrin. And in the second step, we'll add sodium hydroxide to act as our base, and we get an intramolecular Williamson ether synthesis, and so we're going to end up with the same product. So we're going to end up with the same product here. We're going to end up with 1,2-epoxy cyclohexane. Now, for this reaction, we don't have to worry about stereochemistry. Okay, so if you think about the oxygen adding from the other side of the ring, we don't have to worry about stereochemistry for our products, because if the oxygen added from the other side of the ring, they would actually be the exact same molecule, 1,2-epoxy cyclohexane. So we'll save stereochemistry for the next video, where we can focus in on what happens when you're adding an oxygen to different sides of a plane. In the last video, we saw two different ways to form an epoxide from an alkene. The first way was to add a peroxy acid. The second way was to first form a halohydrin using bromine and water, and then using sodium hydroxide to start an intramolecular Williamson ether synthesis to form our epoxide. In this video, we'll look at the stereochemistry of epoxide formation for either of these two reactions. And if we start with a cis alkene, right, so our hydrogen's on the same side of the double bond, or you can think about the R groups as being on the same side. For the product, the R groups are still going to be on the same side of where the double bond used to be. If you're looking at a trans alkene, so I know this is trans, it's my hydrogens are on opposite sides. Right, you think about the R groups being on opposite sides of the double bond, and in the product, the R groups are still going to be on opposite sides of where the double bond used to be. So let's look at a reaction involving stereochemistry. So if I start out with an alkene, and I'm going to put a methyl group here, and I'm going to put an ethyl group over here, and then I'm going to have my hydrogens like that. And if I react this alkene with either of those two reagents, right? So I'll just go ahead and put ditto marks again. So either of those two are going to give me the same products. If I think about the formation of an epoxide, right? So I know I'm going to make an epoxide, and I know I need to have those R groups on opposite sides of where the double bond used to be. So one possible product, right, would be to have the ethyl group coming out at me in space, and then the methyl group would therefore need to be going away from me in space like that. So if that's my product, at this carbon over here on the left, I must have my hydrogen going away from me in space, and at this carbon over here on the right, I must have my hydrogen coming out at me in space like that. So that's one possible product. I could actually draw another product where my R groups are on opposite sides of where the double bond used to be, right? So I could have my ethyl group going away from me in space at the carbon on the left, and I could therefore have my methyl group coming out at me on the carbon on the right, like that. And so this would have a hydrogen coming out at me, and then this carbon would have a hydrogen going away from me, like that. So I have two possible products, and these are actually enantiomers of each other. Okay, so you're actually going to create a racemic mixture, 50% of one enantiomer and 50% of the other one as well, because this reaction creates two new chirality centers, right? So if I take a look at this molecule, right, these two carbons are chirality centers. So there's stereochemistry at both of those carbons. So when you're drawing the enantiomers, right, if I start with that molecule on the left, I have my ethyl group coming out at me. All I have to do is reverse that absolute configuration to make the ethyl group going away from me for the enantiomer on the right. If I'm looking at this chirality center over here, I have my methyl group going away from me, right? All I have to do is reverse that absolute configuration, have the methyl group coming out out at me. So these two are enantiomers of each other. Let's look at the details of the formation of these two enantiomers, and then we'll also name them using stereochemistry. So if we start with the alkene over here on the left, right? So if we're starting with that alkene, and I think about these two carbons, right? These two carbons are sp2 hybridized, meaning the molecule will be planar at those two carbons. So I could think about that alkene as being planar at those two carbons. So if I'm going to go ahead and draw that molecule here, okay? So I'm going to put my methyl group over here on the left, and hydrogen over here, and then I'm going to have a hydrogen over here, and then an ethyl group like that. So it's the same molecule. It's the same molecule as this one over here on the left. It's just rotated a little bit. And I know that those two carbons are on either side of my double bond are sp2 hybridized, meaning that that portion of the molecule is planar, right? So I can think about that portion of the molecule as planar, and I could think, therefore, about the oxygen adding from either side of that plane, right? The oxygen could add from the top of the plane, or the oxygen could add below the plane. So let's go ahead and draw the results of those two different ways of adding the oxygen. So over here on the left, I'm going to think about what happens to the molecule when the oxygen adds to the top of that plane. So if the oxygen adds to the top of the plane, right, I'm going to go ahead and keep my methyl group and my ethyl group on opposite sides of where the double bond used to be. And therefore, the two hydrogens are also going to be on opposite sides of where the double bond used to be. And I'm going to show the oxygen adding to the top of the plane, so therefore my epoxide would look like that. So that's one possible way to form your epoxide. So let's go ahead and think about what would the epoxide look like if the oxygen added from below that plane. Right? So if the oxygen added from the below the plane, once again, we need to think about keeping our methyl group and our ethyl group on opposite sides of where the double bond used to be, like that. And the hydrogens are also going to be on opposite sides of where the double bond used to be, like that. And then we're going to show our oxygen adding to form our epoxide from below the plane. So our epoxide might look like that. So these are my two possible products, and these are enantiomers of each other, but it's kind of hard to see that as we've drawn them right here. So let's see if we can get a different vantage point on our epoxide product. So I'm going to put my eye right here, and I'm going to stare at this epoxide like that. Okay, so if I'm staring at that epoxide, right, I could redraw my epoxide here. So I'm going to put that portion of the molecule like that. Now, if I'm staring at it that way, right, then I'm going to first focus in on the carbon on my left. So that would be this carbon down here. And I can see that there's an ethyl group coming out at me. So I'm going to go ahead and draw an ethyl group coming out at me in space. And I can see that there's a hydrogen going away from me in space, right? Hopefully it's obvious this hydrogen is going away from me in space. So I can represent that. So I'll put my dash in here to show my hydrogen going away. And now we're going to take a look at the carbon on the right side. So this carbon, the other side right here. This time I can see that the hydrogen is coming out at me in space. So I'm going to go ahead and draw the hydrogen coming out at me in space like that. And therefore this methyl group back here, this methyl group is going away from me in space, right? So I can go ahead and show that methyl group going away like that. So that's one enantiomer. Let's go ahead and try to redraw the one on the right here. So again, if I'm staring, right, if I'm staring at this epoxide like that, right, what do I see? Well, I will see the epoxide as being upside down, right? So the oxygen would be down here. And I can see that if I'm looking at the carbon on the left side of my vantage point, right, so that would be this carbon down here. I can see there's an ethyl group coming out at me in space. So here is my ethyl group coming out at me in space, and this hydrogen would be going away from me. So I'll represent that hydrogen going away from me like that. And then if we move to the carbon on the right side here, I can see that this hydrogen is coming out at me in space, so I can go ahead and draw the hydrogen coming out at me in space. And the methyl group back here would be going away from me in space, so I can have the methyl group as a dash, like that. So this is one of my products, and again, it's still not obvious that these are enantiomers. So this is where the model set comes in handy. So if you make this molecule on the right, and then you hold this oxygen and you rotate this oxygen up. Right, much easier to see with the model set right in front of you. You will find that this molecule is the exact same molecule as the one that we're going to draw right here. So if we rotate it so the oxygen is now pointing upwards, that's actually going to take this hydrogen back here and move it to the front. Okay, so when you're drawing that molecule rotated, that hydrogen is going to move to the front, which pushes the ethyl group to the back. So the ethyl group is actually going to the back here. Same thing with this methyl group. This methyl group was in the back. When you rotate it that way, the methyl group is going to end up coming out at you like that. And then that means the hydrogen is going to go away from you in space. So now we can see, hopefully, that these two are enantiomers to each other. And let's go ahead and think about naming this product, right? So if I were going to name these two molecules, I have to think about how to do it. Right, so I need to find my longest carbon chain, and I want to give my epoxy substituent the lowest number possible. So if I'm going to number my carbon chain, I would make this carbon number 1, this carbon number 2, 3, 4, and 5, like that. So I'm going to name it as a pentane base, right? So this would be pentane, like that. And I can see my epoxy occurs between carbons 2 and 3. So it'd be 2, 3 epoxy pentane, like that. So this enantiomer would be 2, 3 epoxy pentane. This one would be 2, so I can go ahead and write 2, 3 epoxy pentane, like that. But now I have to think about the stereochemistry at carbons 2 and 3. So that makes things a little bit trickier. So I'm going to look at the enantiomer on the left, and I'm going to redraw the enantiomer on the left. So I'm going to redraw this one right down here, and let's see if we can start to assign some stereochemistry. So I have my hydrogen coming out at me. I have my methyl group going away from me, like that. This ethyl group is coming out at me. This hydrogen is going away from me. So let's start with this carbon. If I wanted to figure out the absolute configuration at that carbon, I have to think about what atoms are directly connected to that carbon. Right, so let me go ahead and draw a carbon in here. Right, so that is one of the atoms directly attached to that carbon in blue. So the carbon in blue is directly attached to this carbon, this oxygen, this hydrogen, and this carbon right down here. So those would be the 4 atoms. So if I'm trying to determine priority, I think about the atomic number, and I know that oxygen has the highest atomic number out of those 4 atoms, so the oxygen is going to get a number 1. Hydrogen has the lowest priority, so hydrogen gets a number 4. So now I have to think about these 2 carbons, and since there's a tie, I have to think about what those 2 carbons are attached to. Well, the carbon on the right, so this carbon right here, this carbon right here is attached to an oxygen. All right, so let me go ahead and write this here. The carbon on the right is directly attached to an oxygen. It's directly attached, right over here, this oxygen is directly attached to a carbon, and it's directly attached to a hydrogen. So oxygen, carbon, hydrogen. Let's go ahead and look at the carbon on the left, right? So this carbon right here, what is that carbon attached to? It's attached to another carbon over here and 2 hydrogens, so CHH. So the oxygen is going to beat the carbon in terms of atomic number. So this carbon on the right is going to get highest priority. So this carbon is going to get a number 2 here, and that means this carbon is going to get a number 3. So for absolute configuration, my lowest priority group is going away from me, and I'm traveling around this way. All right, so I'm going clockwise, so it's an R absolute configuration at that carbon. Okay, let's go ahead and since that drawing is really busy, let's go ahead and draw it one more time, and we'll figure out the absolute configuration at the other carbon. Okay, so let's see. We still have my ethyl group coming out at me, still have the hydrogen going away from me, still have this hydrogen coming out at me, still have this methyl group going away from me, like that. So if I'm trying to find the absolute configuration for this carbon, we're going to approach it the same way. Look at the atom directly attached to that carbon, so it'd be oxygen, carbon, carbon, hydrogen. So priorities, right? The oxygen gets highest priority, the hydrogen gets lowest priority. And then this carbon over here is directly attached to an oxygen, so this is going to get second highest priority, and that makes this methyl group over here the third highest priority. So the 1, 2, 3 is going around this way, which is counterclockwise, which makes you think it might be S, but remember that trick that I told you about in an earlier video? It looks S, but this hydrogen is coming out at me, so all I have to do is switch that, and that takes care of the fact that my lowest priority group is not pointing away from me. So it looks S, but since the hydrogen is coming out at me, I can say with confidence that is R for an absolute configuration. So we can go ahead and finalize the name, right? So at carbon 2 and at carbon 3, we have an R absolute configuration, so the name of this enantiomer would be 2R, 3R, 2,3 epoxy pentane. And for this enantiomer over here on the right, I know that it's the enantiomer, so I just have to switch the absolute configuration. So this one is going to be 2S and 3S, 2,3 epoxy pentane. And we don't have time in this video to go ahead and assign absolute configuration to the enantiomer on the right, but you can go ahead and do so for practice, and you should get 2S, 3S for its absolute configuration. Now, this is a problem because if you're forming a racemic mixture of your epoxide, that's not always what you want to do in organic chemistry. So there are ways to use chiral catalysts that allow you to select out for one of these enantiomers. And we won't cover it in any of these videos since these are more intro organic chemistry videos, but just be aware that it is possible to be selective in which enantiomer you produce. Epoxides have a lot of ring or angle strain, and this makes them very reactive towards ring opening. So in this video, we'll look at the ring opening reactions of epoxides using strong nucleophiles. So in the first step, we add a strong nucleophile to our epoxide, and in the second step, we add a proton source, and the nucleophile is going to end up opening the ring and adding in an anti-fashion to the OH that is created here. And so in terms of regiochemistry, that nucleophile adds to the least substituted carbon, so it's going to add to this carbon right here. If we go back and look at our epoxide on the left, that's this carbon, and this carbon is attached to 2 other carbons, so it would be classified as a secondary carbon, whereas the carbon on the right is attached to 3 other carbons, and so that's a tertiary carbon. So the mechanism for this reaction is an SN2 type mechanism, which means that our strong nucleophile is going to attack the least sterically hindered carbon, which is the one on the left, since a hydrogen takes up less space than some bulky R group over here on the right. And so that's the regiochemistry here. The stereochemistry is an anti-opening of the ring for an anti-addition of the nucleophile, and this will affect possible chirality centers, as we will see in later examples. Let's look at some examples of strong nucleophiles. So for your strong nucleophile, you could use an alkoxide anion, so something like this over here. You could use a Grignard reagent, which we know are sources of carb anions, right? So we could have a negatively charged carbon like this, and you didn't have to write your Grignard reagent like this. You could have written it like, just showing it RMGBr. Hydride itself is not a strong nucleophile, but if hydride is coming from something like lithium aluminum hydride, it functions like a strong nucleophile. So we could go ahead and show that hydride is really coming from lithium aluminum hydride. So if we go ahead and draw this in here, aluminum is going to have a -1 formal charge, and then lithium would have a +1 formal charge like that. So lithium aluminum hydride is a source of a strong nucleophile. It's just that the hydride anion on its own, we've already talked about, is not the best nucleophile. And then, of course, you could have something like hydrogen sulfide anion, or the hydrosulfide anion right here, which also functions as a strong nucleophile. Let's take a look at the mechanism to form our alcohols here. So we're going to once again start with our epoxide, and I'll use the same epoxide that we had before, meaning there's going to be an R prime here and our double prime going away from us. hydrogen coming out at us, and an R group going away from us like that. So when I think about electronegativity differences, I know that the oxygen is more electronegative than this carbon, for example. So the oxygen is going to pull the electrons in the bond between the oxygen and that carbon closer to the oxygen, giving it a partial negative charge. So pulling some electron density away from this carbon will give this carbon down here a partially positive charge. And so that carbon is going to function as our electrophile. So when the nucleophile comes along, right, so the nucleophile will have a lone pair of electrons and a -1 formal charge. It has two options, right? It could attack the carbon on the left, or it could attack the carbon on the right. And since it's a strong nucleophile, which proceeds via an SN2 type mechanism, it's going to attack the carbon on the left. So once again, the carbon on the left is the least sterically hindered, right? That hydrogen is not very big compared to some alkyl group over here on the right. So the nucleophile is going to attack the electrophile like that, and when that happens, it's going to kick these two electrons in here off onto your oxygen. So we can go ahead and draw the product of that nucleophilic attack. Right? So now we broke our epoxide ring there, and we have an extra lone pair of electrons on that oxygen, giving that oxygen a -1 formal charge. These R groups on the carbon on the right haven't changed, right? So they are still there like that. We've now added our nucleophile like that. And that's going to push the hydrogen up relative to the plane, and then we have an R group over here like that. So the nucleophile has to attack from below because the oxygen is on top, and the nucleophile is going to attack the least sterically hindered carbon. This ends up putting your nucleophile and your oxygen anti to each other. And in the second step, we can add a proton source, so something like water. And we're going to get an acid-base reaction where our alkoxide is going to take a proton from water, which kicks these electrons in here off onto the oxygen, and that will form our final product with an alcohol. So I'm going to have an alcohol right here. And once again, my R groups are still there, so I have R prime and R double prime. Our nucleophile has added, and our hydrogen is pushed up, and our R group is still back here. So that is the mechanism for the SN2 type reaction. Let's do a problem which involves some stereochemistry, so we can see how the mechanism will determine the stereochemistry of the products here. So I'm going to start out. I'm going to put my epoxide coming out at me in space like that. And then at this top carbon here, I'm going to have a methyl group going away from me in space. So that's my reactant, and I'm going to use sodium ethoxide. So we'll go ahead and draw sodium ethoxide here. And we're going to use ethanol as the solvent. So we have ethanol here as our solvent like that. So if we look at this epoxide, it's a little bit hard to see the stereochemistry. So let's go ahead and redraw this molecule, and we'll look at it from a different vantage point here. So if I look at that epoxide from a different vantage point, I'm looking at it from above and down a little bit, and that would put my epoxide going up like that. And then it was this carbon right here that's going to have the methyl group going down relative to the plane of the ring. And then this carbon over here on the left has a hydrogen. So my first step would be to identify my nucleophile, which of course is the ethoxide anion. So I can go ahead and draw my ethoxide anion in here. And next I need to think about where that nucleophile will attack. Right? So I know that this top oxygen here, being more electronegative than the carbons, is going to have a partial negative charge. And so I have two options, right? I could be the carbon on the left, I could be the carbon on the right. And if I think about the fact that this is a strong nucleophile, SN2 type mechanism, it's going to attack the less sterically hindered carbon, which of course is the carbon on the left, which is going to have a partial positive charge. And so we're going to get nucleophilic attack, right? My nucleophile is going to attack this carbon right here, which would kick these electrons in here off onto the oxygen. So I can go ahead and draw the product of that. Right, so I have my ring like that, and I opened up the epoxide ring. So now this this bond is to an oxygen, and it has 3 lone pairs of electrons like that, which give it a -1 formal charge. There's still a methyl group going down at this carbon. And I've added my nucleophile to this carbon, so I can go ahead and draw my oxygen and then an ethyl like that. And then I pushed up the hydrogen. Right? So when this reaction occurred, the hydrogen that was down relative to the plane of the ring got pushed up. So now there's a hydrogen up at that carbon. And in my final step, right, I'm going to protonate the epoxide. So lone pair of electrons will pick up a proton from ethanol, which kicks these electrons off onto here. And I form my alcohol as my product. Right? So when I'm drawing my product over here, now I have an OH, and I still have a methyl group going down. And over here I have an oxygen and then ethyl like that. So if I wanted to draw my product as a 2-dimensional dot structure, right, I could look this way. I could look down on it like that and just go ahead and draw what I see when I'm looking down. So I can draw my ring. So here is my ring, and if I look at this carbon right here, there's an OH coming out at me. So I can represent the OH coming out at me with a wedge right here. And there's a methyl group going away from me at that carbon. So this methyl group is going away from me. So I can go ahead and put in a dash for that methyl group. And when I look at the other carbon here, right, I have an O and then an ethyl going away from me. So I have this guy would be a dash going away from me like that. So that, of course, is this portion of the molecule. So that's my product. When I look at what happened to the stereochemistry, let's first start with this top carbon right here. This top carbon had a methyl group going away and an oxygen coming out at you at that carbon. And if we look over here, that's the same thing that we have. We have a methyl group going away from us and then an oxygen coming out at us like that. So it's the same absolute configuration at that carbon. If we look at the other carbon, if we look at this carbon down here, on the left we had an oxygen coming out at us in space, and on the right at this carbon, now the oxygen is going away from us in space. So we actually see inversion of configuration, right? So right here we have inversion of configuration in terms of the stereochemistry. We went from a wedge to a dash, and that's of course due to the mechanism. Okay, we had a nucleophilic attack at a chirality center, and so we observe inversion of configuration at that chirality center. Let's do one more example of a strong nucleophile attacking an epoxide, and so this time let's use a Grignard reagent. So I'm going to start with phenyl magnesium bromide. So we've already made phenyl magnesium bromide as our Grignard reagent, and in the first step we're going to add ethylene oxide, right, the simplest epoxide. In our second step we're going to add hydronium, so H3O+, and that'll be our source of protons, but that has to be in a second step. You can't add that at the same time, because there'd be an acid-base reaction from your Grignard reagent with your hydronium ions. So if I'm looking at phenyl magnesium bromide, I could draw it like that, or I could redraw it to identify my carb anion, right? So if I think about what's going to happen, the electrons in the bond between this carbon and magnesium in here, carbon is more electronegative than magnesium. So you could think about those two electrons as being on that carbon, like this, which would give that carbon a -1 formal charge. And so now we have a carb anion, and then we'd have MgBr plus like that. And that's going to be the nucleophile. When we have our ethylene oxide that comes along, right? So same idea. Oxygen's more electronegative, so partial negative on the oxygen and a partial positive on the carbons. They're symmetrical. So when I think about nucleophilic attack, right, these electrons in blue are going to be my nucleophile. They're going to attack my electrophile, kicking these electrons off. So when I draw the product of the nucleophilic attack, I have my ring here. And now I'm going to end up with an alkoxide that looks like this. Okay, so let me go ahead and highlight the electrons in blue. The electrons in blue formed a new bond, a carbon-carbon bond right here. So the electrons in blue formed a new carbon-carbon bond, which is why organometallics are so useful, right? You can form these carbon-carbon bonds here. And then I can see that the two carbons over here on the right, this carbon and this carbon, those are the ones that came from my ethylene oxide like that. So in my last step, right, it's an acid-base reaction, and this alkoxide is going to pick up a proton from H3O plus in the second step. So lone pair of electrons picks up a proton, kicks these electrons off, and I can go ahead and draw the product. Right, so once again, here's my ring, and I now protonated my alkoxide to form an alcohol. And the name of this alcohol, right? So if I think about this as being carbon 1 and this as being carbon 2, I have a phenyl group coming off of ethanol. So 2-phenyl ethanol would be the name of the product that's formed. And 2-phenyl ethanol is famous for being a component of rose oil. So this molecule smells a lot like roses, and it's used in the perfume industry. So this is one way to make 2-phenyl ethanol. There are actually several ways to do it, but I think perfume chemistry is extremely interesting. Here's the general reaction for a ring opening of epoxides when everything is acid catalyzed. So if I first start by looking at my epoxide over here on the left, I can classify this carbon, and I can see this carbon is attached to 2 other carbons, so this carbon would be secondary. Or I could think about a hydrogen replacing that R group, and then it would be a primary carbon. So either primary or secondary. If I look at the carbon on the right side, so this carbon right here, it's attached to 3 other carbons. So this carbon on the right would be tertiary. So if I react this epoxide with a weak nucleophile, so HNU is going to refer to my weak nucleophile, and I make it an acid catalyzed reaction, I can see the product over here on the right. The nucleophile has added to the most substituted carbon. So here I can see my nucleophile. I added to my tertiary carbon over here on the right. So that's the regiochemistry, nucleophilic attack of the most substituted carbon. And I can see when the ring opens, the OH group is going to be anti to the nucleophile. Let's take a look at a reaction, and we can run through the entire mechanism for this ring opening. So if I start with my epoxide, so I'll go ahead and make it like this. I'm going to have my epoxide coming out at me in space, and then at this top carbon here, I'm going to have a methyl group going away from me in space. So here's my methyl group. I'm going to react this epoxide with ethanol. So I'll go ahead and put ethanol in here. Ethanol is going to function as my weak nucleophile, and it's acid catalyzed, so I'll make sure and put my protons in there like that. Okay, let's go ahead and redraw the epoxide so we can see it a little bit better. So we're going to be looking down on our epoxide like this. So therefore, the oxygen is going to be up relative to the plane of the ring. Lone pair of electrons on the oxygen like that, and then at this carbon there's going to be a methyl group going down in space. The first step of the mechanism is an acid-base reaction, right? This is an acid catalyzed reaction, so there are H plus protons floating around. Lone pair of electrons on oxygen are going to pick up that proton, so I'm going to protonate my epoxide. So when I draw the product of that acid-base reaction, and I now have, on my oxygen, I still have 1 lone pair of electrons. The other lone pair formed a bond with that proton, so now it is a protonated epoxide, which gives the oxygen a +1 formal charge. I still need to have my methyl group down relative to the ring like that. Now, when I think about the next step, I need to think about the classification of the carbon atoms. So if I look at this top carbon right here, I can see that this one is attached to 3 other carbons. So this is is my tertiary carbon. The one down here is only secondary. And I know the nucleophile is going to attack the more highly substituted carbon, which would be this one down here, like that. So this is the carbon that's going to get the attack. Now, if I think about that oxygen being positively charged, oxygen doesn't like to be positively charged. Oxygen's very electronegative, so it's going to do its best to pull some of these electrons in the bond between that carbon and that oxygen a little bit closer to the oxygen there. So I'm going to withdraw some electron density from this carbon. So this carbon is going to end up having a partial positive charge, like that. And if I think about what kind of a carbocation would that be, it has a little bit of partial carbocation character, and I can think about the fact that that carbon is attached to those 3 other carbons, right? It's a little bit easier to see here. There's 1, 2, and 3 other carbons. And in earlier videos, we've seen that tertiary carbocations are the most stable, much more stable than secondary carbocations. And if I have a weak nucleophile attacking, it's going to attack the most substituted carbon. So it's going to attack the one that would be the most stable carbocation. So again, we have more of a partial carbocation character here, but when the weak nucleophile comes along, right, that lone pair of electrons is going to attack this carbon right here, and that is going to kick these electrons in here, the magenta ones, off onto your oxygen. So let's go ahead and draw the result of that nucleophilic attack. So I have my ring right here, and I've opened my epoxide. So now this oxygen is going to swing over to the left here, and it has it's bonded to a hydrogen. It had 1 lone pair of electrons. It just picked up 1 more lone pair of electrons, the magenta ones. And in the course of that nucleophilic attack, the methyl group that's down relative to the ring here gets pushed up. So the methyl group will end up relative to the ring. And I have a lone pair of electrons from the ethanol molecule that are now bonded to this carbon, so I can go ahead and show those electrons. And there's an oxygen, a hydrogen, and then 2 carbons, and then there's still a lone pair of electrons left in that oxygen, which gives that oxygen a +1 formal charge. So let's just go ahead and highlight those electrons really fast. So let's see, I'll make them red here. So these electrons right here, those are the ones that attack the carbon, and those are the ones that formed this covalent bond, like that. So we're almost done. The last step will be an acid-base reaction to get rid of that +1 formal charge on the oxygen. So another molecule of ethanol comes along. This one's going to act as a base. So I go ahead and draw another molecule of ethanol, and it has lone pairs of electrons on it. One of those lone pairs of electrons are going to pick up that proton, which kicks these 2 electrons off onto this oxygen, and we're going to end up with our product. So let's go ahead and draw the product right up here. And like usual, we're going to be looking down on our molecule this way. And so we're going to look down right here and draw what we see. So we're going to have our ring like that. And at the top carbon, which would correspond to this one right here, I can see that there's a methyl group coming out at me, so I can go ahead and put my methyl group coming out at me like that. And then going away from me, I'm going to have my oxygen. So I'm, of course, talking about this oxygen down here like that. So I can go ahead and draw that oxygen going away from me, and connected to that oxygen, of course, would be 2 carbons. So I can go ahead and do that. And when I look at the carbon on the left over here, so now I'm talking about this carbon, I can see there's an OH group coming out at me in space, so I can go ahead and put that OH group coming out at me in space right there. So that's going to be our product. So again, I went ahead and showed, I can go ahead and put my 2 lone pairs of electrons on that oxygen, because I showed that proton being removed in the last step of that mechanism there. So let's look at the stereochemistry, and let's first start with this top carbon here. So I go back to my reactants and I look at this top carbon, and I think about the fact that I have a wedge to an oxygen, right? So oxygen's coming out at me and a carbon's going away from me in space. When I look at my products, right, this would be the carbon that corresponds to that carbon. It's the opposite, right? Now I have a carbon coming out at me in space and an oxygen going away from me. So that's inversion of configuration. So at that top carbon there, so at this carbon right here, I'm going to get inversion of configuration. So inversion of absolute configuration here. So let me go ahead and write that. Inversion of configuration. Okay, so there's some stereochemistry involved. And when I look at the other carbon, right, so when I look at this carbon down here, I can see that there's an oxygen coming out at me in space. And when I look at that carbon for my products, I see there's still an oxygen coming out at me in space. So it's the same absolute configuration at this carbon. So we only see inversion of configuration at the carbon which is undergoing the nucleophilic attack, which is the most substituted carbon. Let's look at how to prepare sulfides from thiols. So over here on the left, I have my thiol. And to that thiol, I'm going to add sodium hydroxide. And the sodium hydroxide is going to deprotonate the thiol, which is then going to react with this alkyl halide in the second step of the reaction to produce my sulfide as my product. So here's my sulfide right here. This reaction is the analog of the Williamson ether synthesis, which we've seen in an earlier video. So in that video, we started off with an alcohol, and we reacted our alcohol with a strong base in the first step and an alkyl halide in the second step, and we formed an ether as our product. So we can go ahead and draw our ether in here like that. So the thiol is the sulfur analog to an alcohol, and a sulfide is the sulfur analog to an ether. Let's look at the mechanism to make sulfides. So if I start with my thiol right here, so I have carbon bonded to sulfur, bonded to a hydrogen, and then two lone pairs of electrons on that sulfur. And if I think about the difference in electronegativity between carbon and sulfur, there's actually not much of a difference in terms of numbers. So this is not a very polar bond, actually. That's different from what we see with an alcohol. So up here, if we look at the alcohol, I know that oxygen's much more electronegative than carbon, so this oxygen here would get a partial negative, and this carbon on the left it's bonded to would get a partial positive. So there's much more of an electronegativity difference in alcohols. In thiols, there's not really that much of a difference. But thiols can still function as nucleophiles because these lone pairs of electrons are located further away from the nucleus than the lone pair of electrons on oxygen, because sulfur is a larger atom. So those electrons are more polarizable, and so thiols are actually excellent nucleophiles. So if we go back here to our mechanism, right, we're now going to add sodium hydroxide, which is a base, so we can go ahead and put OH minus over here. So the hydroxide anion is going to function as a base, and a lone pair of electrons are going to take this proton and leave these electrons behind on the sulfur. So let's go ahead and draw the conjugate base to the thiol. So we now have carbon bonded to sulfur, and this sulfur now has three lone pairs of electrons, giving it a -1 formal charge. So this is called a thiolate anion. So let me just go ahead and write that. A thiolate anion in here. And thiolate anions are very stable. That negative charge on the sulfur, since sulfur is a large atom, you can spread out that negative charge over a very large area. So the thiolate anion is relatively stable, and that makes thiols more acidic than alcohols. Okay, so alcohols don't have the same type of stabilization since alcohols are smaller. So thiols are actually very acidic, and that's why we can use sodium hydroxide here to deprotonate our thiol to form the thiolate anion. In the second step, right, we add our alkyl halide, and so here's my alkyl halide. And the alkyl halide does have a polarized bond, right? The difference in electronegativity between a halogen and a carbon atom is fairly large. So this halogen here is going to get a partial negative charge, and this carbon is going to get a partial positive charge. So thiols are good nucleophiles. Thiolate anions are even better nucleophiles. And so the thiolate anion is going to function as the nucleophile. The partially positive carbon is going to function as the electrophile, and we're going to get an SN2 type mechanism, where our strong nucleophile attacks our electrophile and kicks these electrons off here onto the halogen, and we can go ahead and form our product, right? So this is an SN2 type mechanism, and we end up with the sulfur, right, now bonded to two R groups. And they could obviously be the same R groups or they could be different R groups. And so we formed our sulfide like that. Let's do an example of the preparation of sulfide. So we're going to start with, let's start with this one right here. All right, so we start with this molecule, and to that thiol, we're going to add sodium hydroxide in the first step. So let's go ahead and write sodium hydroxide here, Na plus, and then OH minus, like that. And then in the second step, we're going to add an alkyl halide. So let's add this as our alkyl halide. So ethyl bromide. So when I think about the mechanism, right, I know the first step is an acid-base reaction. The electrons on the hydroxide anion, so one of these electron pairs here, are going to take this proton, that's the acidic proton on my thiol, leaving these electrons behind on the sulfur. So I can go ahead and draw the resulting thiolate anion. So I can go ahead and draw that. Let me see what we have here. We have our ring, and then we have our sulfur, and our sulfur now has 3 lone pairs of electrons around it like that. Thiolate anions are excellent nucleophiles. And when I look at my alkyl halide, once again, I know the electronegativity difference between bromine and this carbon here are going to give bromine a partial negative charge, and this carbon is going to be partially positive. So the thiolate anion is going to act as a nucleophile in an SN2 type mechanism, and a lone pair of electrons here are going to attack my electrophile, and we can go ahead and form our product, right? So now we have our ring here, which is connected to our sulfur, and our sulfur now just picked up 2 more carbons, right? Because these electrons in here are going to kick off onto the bromine, and we end up putting an ethyl group onto that sulfur. So there are 2 carbons now on that sulfur like that, and the sulfur has 2 lone pairs of electrons. And so we formed our sulfide. Now, if I were to name this sulfide, it's a lot like naming ethers. So I could use the common way of naming this and treat those as alkyl groups. And if I look on the right, this would be an ethyl group. So I could go ahead and start naming it. I could say it's ethyl. And if I look at the alkyl group on the left side, right, this is a phenyl group right here. So it's ethyl and then phenyl, since I'm following the alphabet rule here, E before P. And then finally, I know it's a sulfide, so I can just go ahead and finish the nomenclature by saying sulfide here. So ethyl phenyl sulfide is the sulfide produced in this analog of the Williamson ether synthesis.